Hey everyone, so let's solve today's LeetCode POTD pyramid transition matrix. So the problem states that we are starting blocks to form a pyramid. Now each block has a color which is represented by a single letter. Each row of blocks contain one less block than the row beneath it and is centered on top. So for example, the pyramid will look like something. We have a block like this, then these blocks, then 3 blocks in next row, then 4 blocks in next row, and so on. Okay, so this is a pyramid. Now to make the pyramid aesthetically pleasing, there are only specific triangular patterns that are allowed. So this triangle, then this is a triangular pattern, this is a triangular pattern, this is a triangular pattern, and all of these are triangular patterns. So there are only specific triangular patterns that are allowed, and a triangular pattern consists of a single block stacked on two, means a single block is stacked on top of 2 blocks. So this is forming a triangle here. Okay, now the patterns are given as a list of 3-letter strings allowed, where the first 2 characters of a pattern represent the left and right blocks. Means the first character is this. Suppose this is the pyramid. So the first character is represented by this, second is this, and third is this. So we are given allowed strings in this form. First character represents this, second this, and third this. Okay. Now, and the third character is the top block. For example, ABC represents a triangular pattern with C block stacked on top of A and B. Okay. So note that this is different from BAC, where it will be B, A, and then C. Okay. So I hope the problem is clear. Now we start with the bottom row of blocks bottom given as a single string. We must use as the base of the pyramid. So we are given the base of the pyramid in the form of this bottom string. Now given bottom and allowed, we need to return true if we can build the pyramid all the way to the top such that every triangular pattern in the pyramid is in allowed. So now since suppose this has length L, so this will be means we will be placing L minus 1 blocks here, right? And then L minus 2 and till 1. So we need to tell whether it is possible to build this pyramid such that every triangular pattern that we will be forming is present in this allowed list. Okay, for example, this allowed list, this is how the triangles will be forming. So we need to tell means if we are able to form the pyramid such that all the triangular patterns are in this list, so we'll return true or false otherwise. We are given that the length of bottom can be at most 6, so the bottom length can be at most 6, and the allowed length can be 2 to the power 16 because we have 6 characters, 6 character that can be present, and we have 3 means allowed length will be 3, so 6 into 6 into 6, so it is 216. So the maximum possible length for allowed is 216 because it can only have 6 characters, and all the values of allowed are unique. Okay, so let's see the given input. So we are given the bottom as B, C, D. Now I can fill either A here or B here or C here. Let's try to fill A. If I fill A, then BCA is not in the list. So this is not good. Then if we try to fill B, BCB is also not in list. BCB is not also in list. So we will not fill C. BCC. So we see BCC is present in the list and it is a valid triangle. So we'll fill C here. Now let's see CD. So for CD, we have E in that. So let's try to fill E here. So this triangular pattern CDE is present in the allowed list. Now for CE, we have A. We can simply fill A here. So we'll have CEA. So we saw like we are able to form a triangular pyramid because like we have BCC in the list, CDE in the list, as well as CEA in the list. Okay. So hence in this case, the output will be simply true. Let's see another input. So we are given the bottom as A. So what we can fill here, AAA we can fill, but it is not present. AAB we can fill. So let's fill it. AAC we can also fill. So either we can fill B or C. So we see like we have BC here. So let's try to fill C here. Okay. And then we can fill, let's say we have B here. So let's try to fill BB only. B. So we see like AAB, all are in allowed list. Now we have BBE. So BBE we can fill. BBE again we can fill. Now do we have something with EE? We do not have. So we'll not be able to create a pyramid, means we'll not be able to fill this position with some character such that EE and this character is present in allowed list. So this is not valid. Let's try another possibilities. So we can see like we have B, C, B. So we can BCD, but again CB is not present. Okay, so we'll not be able to fill this as well. So we'll try for all possible ways and we'll see like there exists no possible ways of developing this pyramid, and hence in this case the output will be simply false. So what we can do in this scenario is the brute force approach would be to simply start from the bottom row. Okay, try means if this is of length L, try for all possible next rows of length L minus 1, and then try for all possible means upper rows of length L minus 2 and so on till 1. Okay, and then see like whether means the one possible way of this was true or not, means we are able to develop or not. If you weren't, then we simply return true. Okay, so we can do this in brute force manner. We know like the number of allowed characters can go up to 6, at most 6. So this will be like 6 k power L minus 1, then 6 k power L minus 2, and since it will be recursive, so we'll be multiplying all those factors. Okay, so it will be simply what 6 k power means 1 plus 2 plus till L minus 1. So it will be 6 k power L into L minus 1 by 2, and this L that we have can go up to what means L is simply starting from the bottom length can be 6, so it will be at most 5. So it can be suppose if we start from the bottom factor as well, so approximately suppose it is 36 square by 2, which is 18. So it will be order of 6 k power 18, let's say 2 k power 18 into 3 k power 18. So obviously this will take a lot of time and will not be able to like means we'll be getting clearly in this case. So let's first see this approach of like a brute force approach, then we'll try to means do some optimization. What we'll do, we'll start with the bottom string. Now if the current row has length m, we generate all possible strings of length m minus 1 using the alphabet which are means given in the allow. So a, b, c, d, e, f. We'll try for all these alphabets, and there are 6 ki power m minus 1 such strings, because currently means in the current string we have m. So for m minus 1 length, each position has a means has 6 possibilities, so it will be 6 k power m minus 1. Okay, now for every generated string, check if it can legally sit on top of the current row according to the means allowed list. Okay, so we'll be checking the allowed list and see whether this string that we have generated can sit on this top, and then we'll recursively call the next row. Okay, so we can simply if a generated string is valid, recursively attempt to build from that string. So we'll now build from this m minus 1 length to build m minus 2 length string. Okay, so we can simply do that till we have reached m equals to 1, and in that case as soon as we reach m equals to 1, we'll be able to simply return true, because this would have been a valid way of placing that. This is why we have called a recursion. So in this manner we'll be calling the recursive function and we'll be done. So for means we know like to store like what characters can sit in this value, we can simply store means create a vector 2D vector of size 6 cross 6, and what it will represent, it will represent that if we have means suppose AB, so what characters can sit on top of it. If the allowed list contain ABC, ABD, ABE, so it will be having C, D and E. So we can simply maintain this transition vector so that it is easier to see like what characters can sit on these adjacent pairs, because we will need to check it and then we can simply recursively build. So let's see the code, then like the entire implementation will become much clearer. Okay, so what we'll do, we'll have the pyramid transition. So we'll means this transitions string 2D vector we have created as a global vector. What you'll do, for each allowed string, so we'll see like this u is this, v is this, and the w is simply present this. So we will simply update the transitions of uv with b. Means this w is part, suppose it was ab, so it will be having c, d, e. If the transition allowed string had abc, abd, and abe. Okay, so for AB adjacent pairs, we can stack C on top, D on top, and E on top. Okay, now once you have means that these transitions clear, we'll simply call the solve function with this bottom string and we'll try to recursively build the function. Okay, so let's see the next step. We have this global string adjacency matrix to store all allowed transitions, and it will be list of characters that can sit on top of A and B. So this is what T of A, B represents. Now as soon as this row dot length becomes 1, we know like we are able to stack this character on the previous row, and now we are calling the recursive function for this particular row. So since this is of length 1, that means we have reached top of the pyramid, so we'll simply return true. Now if we are at a length m, so we need to generate all possibilities of length m minus 1. Okay, so we'll generate the next row. So we'll generate means we have created this next rows which will be storing all the possibilities, and now we will be generating it. Okay, so currently we are on this row. Okay, we have the bottom string as this row. We have the current we will be having the current index as 0 because we are currently on the start of the string, and we have means the current string that we have generated is empty current build, and we'll be storing it in this next row. Why we are doing it? Because we will be recursively forming all possible strings, all possible permutations in this of length m minus 2. So as soon as this index equals to row dot length minus 1, that means m minus 1 length we have got, we'll simply push it in our result string. Okay, so we'll simply push it in our result string and simply return. Now for the current index we want the u as index, and we will be simply index plus 1. So we have these uv's. So for all uv's we'll call the recursive function for the w's. Okay, so for all characters that can be on top of this transitions uv, we'll fill it, and then what we'll do, we'll simply move to this index plus 1, so that the v, and then we have new character, suppose x. So for vx we'll try for all possibilities of this w2. Okay, and in this manner we'll be able to build this next string. Okay, so in the next step we'll generate the next rows. For keeping the same row, we'll increase the index, and the increase means we'll push this current top as part of the current build, because we have built w1 here, and now we'll move to bx, then we'll build w2. Okay, and in the end, as soon as this index reaches means the m minus 1, that means we will be simply pushing it. Now once we have all of these next rows contains all of the permutations of the valid strings on the top, then we'll simply iterate through this, and we'll see, like, again call the solve function for this row. Okay, so you call the solve function for this row, and if means it will be recursively called at each step, and if finally it returns true, then we'll simply return true. Okay, so if this is returning true, then we'll simply return true. If none of the rows means none of the valid permutations were possible, then we'll simply return false. So this will be like the recursive approach to solve this problem. We saw the time complexity of this can go up to what? Can go up to 6 ki power n square, 6 ki power n square by 2. Okay, because at each step we had 6 possibilities, and it will be like recursively multiplied, so it will be 6 ki power n by 2. Okay, n square by 2, which will be obviously giving us TLE. So let's try to submit this approach here and see whether it gives TLE or not. This is the same approach. We call the solve function, then generate all the next possible rows, and based on these next rows, we will be having the means we'll be trying for all the possible top transitions, and then currently means building the next row. Okay, so let's try to submit it and see whether it gets accepted or gives TLE. Obviously, like the time complexity is pretty high, so this should give TLE. Let's see, it is loading. It is taking a lot of time. That means it will be not getting passed in some of the test cases. Yeah, so it gives TLE in like the bottom length is 5 only, and yeah, so bottom length is 5. That means it will become what? 6 ki power 5 square by 2. So 6 ki power 10 only. So 6 ki power 10 will be giving TLE here. So let's, how do we like optimize this approach? Why we are getting TLE here? So we know like how we are getting TLE, because we are currently multiplying. Means if we have generated the result for this length L, we have generated the result for L minus 1 as 6 ki power L minus 1. Then we are not storing the result for this row. If we have calculated the result for this row, we do not know whether it is returning true or false. We are in a brute force manner, means trying for all possibilities of 6 ki power L minus 2. That's why the time complexity was getting increased means by products. But instead of that, we can simply create a map of string comma bool, which represents that for this string whether the recursive function returns true or false. Okay, so that if we have this particular string, then we'll only calculate the result for this particular string, means only once. Okay, so what we'll do, we'll simply memorize the result. Memorize. So the approach means entire code will remain the same. What we'll do, we'll optimize the approach with memorization. So we'll simply create this map of string comma bool, and now this will denote like if we have this as the current string, means this as the current row, then whether we are able to reach the top or not. If we are, then we will simply return true, else false. And this will be means solving a lot of subproblems. Suppose we are at the bottom string, and after trying means a lot of permutations, this string remains constant. So obviously we will be solving it once only, means we will not be solving it multiple times based on the means the way that we have used to reach this string. Okay, so we'll be solving it once only and we'll be done. So obviously in this case, what will be time complexity? It will be 6 ki power, means the number of states that we have. So it will be 6 ki power L minus 1 plus 6 ki power L minus 2 plus 6. Okay, so it will be what? Approximately it will be 6 ki power L. Okay, and L can go up to 6 cube power 6. And we have means at each inside each solve function, what you are doing, we are generating this next rows function. So what will be the time complexity of next rows function? So again we have this L length, so this will be like having again 6 possibilities that we have of transitions. So it will be also have a overall complexity of 6 cube power L. So overall like 6 cube power L plus 6 cube power L, so this will be 6 cube power 2n, means n can is also, so it will be 6 cube power 12, which will be 2 cube power 12 into 3 cube power 12, so it will be getting accepted. Okay, so the overall complexity here would be k, which is the number of allowed characters, and it will be 2n. N is the length of the bottom string. Okay, so this will be the overall complexity, and we'll simply means the everything else will remain the same. We can simply create a memoized value and see like for the current string, if the result has already been calculated, we'll simply return it, and in the end while returning we'll update our memo, means update our memoized map. So what will the solve function look like? This void generate next rows remains the same. This everything else remains the same. We have created this unordered map of string comma bool map to store results for row strings we have already solved. Okay, so if the current string for the current row string, if the value is true, we can reach the top. If it is false, then we are not able to. And if that result has already been calculated, we'll simply return it. And while means updating returning, we'll simply update our memoized solution. Okay, so in this manner we will be simply able to transition from this brute force approach to the optimized one. So I hope like you were able to see like only a single line change we needed to do from the recursive approach. So the recursion approach was important here. How we try to generate these next rows based on the transitions of each means pairs, and recursively build this current build, and then in the end push this in our result. So this was important here, and like I hope you were able to follow along. Let's try to submit this optimized code here. We have just included this memo function here, and it should get accepted now. Initially it means gave TLE on 62th test cases only, so test cases are weak, and it runs in beats 63% of the solution. So this is like the most optimal approach to solve this problem. So yeah, this problem was purely based on backtracking and recursion. So if you're able to nice understand the concepts behind it, then make sure to like as well as subscribe. And if you yet have any doubts remaining in any of the parts, then make sure to comment down. I will be happy to respond. Thank you so much for watching.